Okay. Hello, everybody. This is the third kind of workshop in our electronic fundamentals class or workshop. So today we're talking about transistors. So last week we talked about diodes, which are the most kind of basic semiconductor that there is. I talked a little bit, probably more than I should have, about how they work, but just remember the basic components we've kind of covered so far are resistors, capacitors, inductors, and diodes. A resistor is kind of like a narrowing of flow. An inductor is basically a flywheel. It resists a change in flow through it and stores energy in order to release it. And capacitors are kind of like an inflatable bag of electrons that you can squeeze them back out once the pressure voltage on the outside is kind of removed. And finally, diodes are basically check valves, which is to say that it lets current go through in one direction and does not allow reverse flow unless you break it. Transistors are like solenoid operated globe valves, which is the best mechanical analogy I can make, but I recognize that that probably means nothing to you guys. So we talked very briefly with inductors about solenoids. Solenoids are just inductors that can be used they create a magnetic field, and you can use that magnetic field to like pull something, or push something. So solenoid operated in this case means you apply voltage and it opens the valve, or shuts the valve technically, but in the diagram it's open. So you can see that the coil is not energized, this valve is shut, there's no flow. When the coil is energized, there is flow. Gate valve just means you're not doing a good job throttling. It's kind of like, imagine if you just have a gate, right? It's kind of not that well controlled flow. So we're going to first talk about the most common form of transistor, which is the MOSFET. MOSFET, it's not important that you know what it stands for. It does stand for metal oxide semiconductor field effect transistor, or metal oxide, yeah, semiconductor field effect transistor. Field effect, schematically, is represented by this line right here, not being in contact with these lines. You'll see some other transistors that we'll talk about later, which this incoming line does connect here, and that is one of the primary differences. So what you should take away from field effect is there is no path for current from this side. And what that means is this is purely voltage controlled. The presence of the voltage creates an electrical field which operates this. Going back to this being a gate valve, what this does is when voltage is applied to this, it permits current flow here. This is kind of like a diode that will work it depends on the transistor, but will work usually in both directions, but you get to tell it when to turn on and off. And we'll look at some more stuff like that later, but this is a way of remotely controlling electron flow. That's what I want you to take away from MOSFETs. These are 99.9% of all transistors. This is slightly disingenuous because every CPU, every processor is literally just trillions of MOSFETs, all on literally a nanometer scale. If you're talking about discrete components that aren't just a processor that is a million MOSFETs, it's a little less cut and dry. A lot of people will use different types of transistors that we'll cover later for other reasons. They have other like nice characteristics. But again, the big takeaway is the most common type of transistor is the MOSFET, and that transistors are a way to remotely tell a circuit when to allow current. So if you think about anything that we've looked at so far, all the stuff we've seen about like RLC tank, some of the stuff we'll look at today, it can be as simple as just saying, I don't want this circuit to always be operating, and I want to turn it on and off using voltage. And the final thing I'll say about this is, for field effect transistors, where you don't have a direct connection and there is no path for current, this has ideally infinite resistance, impedance. Impedance is, you guys know, but impedance is kind of just resistance, but also incorporating resistance to induction and capacitance, which is kind of beyond the scope. But for now, just think nothing flows through here. You can literally just provide a voltage potential to this, and that will cause it to turn on. So, you know, we don't directly cover this in our slides, but if you think back to the LC tank we showed in our first lesson, and we said, hey, this can't provide useful power, but it can rapidly oscillate and create like a changing voltage. Well, that would be perfect for this, right? We can't use that power, but we can use that power without actually removing any energy from the system to just turn this on and off. And now you're actually cycling actual power at the frequency of your tank. So there's two types of MOSFETs, enhancement and depletion. Enhancement has gaps, which in the context of a gap means there's no path for current. So what you should think of when you think of enhancement is that it is normally not conducting. So in a valve equivalent, it is normally shut. There's nothing going through it. Depletion is the opposite. You can see that there is a path for current flow already in there. That means it's normally allowing flow, so it's like a normally open valve. And when you apply a voltage to it, it shuts. So those are the big ideas. It's important to know that you can have a normally open or normally shut kind of channel, but you know, it's because you may need it for certain applications. But again, the particulars of it are kind of not important. Just know that you can have ones that are normally conducting or normally not conducting. Are there any questions about this before we move on? Okay, great. Okay, so we're going to move into immediately the most simple version of or a simple application of a MOSFET that is very directly applicable to what we might be doing with the reaction wheel. This is what's called a boost converter. There is an equivalent called a buck chopper, but what this does is it will take a voltage and make it higher. So the end output of this is it's like 17, it stabilizes about 17 volts it looks like. Well, no, that was the peak, sorry. Looks like it's mostly around 15 volts. This GIF is a little too fast for my taste, but we're gonna try to break this down. This is one of the last times that we'll be able to kind of do an electron by electron basis. So remember that an inductor is acting as a flywheel. When you turn this on, so this is just saying we have a 1 kHz signal. It is turning this MOSFET on and off 1,000 times a second. When it's on, you have a short to ground through this inductor. So if we remember what an inductor does, it is going to resist that changing current, and then when but it's going to build up a field. You're spinning up your flywheel, you're saving energy. During that period, well, we'll start from nothing, right? We'll say at the very beginning of this, it turns on, it's short to the ground. You're going to build up this field, and then this is going to turn off. So our new path for current is going to be this way. For reasons that are sort of very important to the operation of this, but the depth is more than we're going to cover in this workshop. When you're shorting, what's the easiest way to say this? The time in which it takes to charge this and discharge this is a function of its inductance and the resistance. Which is to say, the higher the inductance, the higher the resistance, the slower it will charge or discharge. That's probably the easiest way to say it. So it's probably easiest to relate this to, let's see, time charge, DC, is proportional to resistance, maybe time charge discharge. So when the MOSFET is gated, is I guess the best technical term for it, when voltage is applied to it. T, yeah, you're right, I should probably like curve that or something. Yeah, so time charge discharge is proportional to resistance. When you're shorting it to ground, resistance is 0. So No, that was right, yeah. No, that was right, okay. So if resistance is 0, your time required to charge and discharge is incredibly short. It charges very, very fast. You store a lot of energy very quickly.
So it's like the e to the negative t over tau, right?
Exactly, it's the time constants. So yeah, if you're familiar with the time constants, then that's literally what this is I just felt it was more effective to just do a proportionality and do this qualitatively. But when you put it in, when you put the loaded circuit, so when the MOSFET is not gated, when it is not conducting, now your circuit has actual resistance in it. So let's say on, your time constant is effectively 0. Off, your time constant is not 0, is really all we care about here. So what that means is you're effectively in this first cycle, so we're going to mark this as one cycle with this being on and this being off. And for the sake of this, although this isn't necessarily accurate, we are going to assume it is on and off for the same length of time because it still functions for our purposes. So it's going to charge very, very fast in a logarithmic pattern while it's on. Which on, I should define this, on is the MOSFET is gated, right? So on equals MOSFET conducting.
And conducting means it's going to ground, right?
Yes, it means it is allowing current to flow through it. So off is MOSFET not conducting, for lack of a better way to say that. You get the point. Now, once it turns, I kind of misaligning this, bros. Let's say on, off. Not mind the dash lines, but so charges very fast, discharges slower. All right, so that is one cycle of on and off. When it's off and the path for flow is through this capacitor is going to begin to charge up. In addition, this thing is once really high current, but it's now getting less, like it wants to be at a lower current from where it's been. So your flywheel now, you've spun it up ridiculously fast, but the new equilibrium with resistor in there is spinning a little bit slower, lower current. Like imagine if this inductor wasn't here, insanely high current, not so much current, right? So it wants to move towards that new lower current, but it has a lot of energy it needs to shed to do so. So what happens here is this has some voltage that is adding to this because it's discharging more electrons than it's being put into it. So you have this cumulative stacking effect of electrons, and that is going to play, that along with the longer time of discharging is basically the main point here. So the next time it gates the MOSFET, it's voltage and time, I should define that. The next time you gate it on, it hasn't even fully dissipated yet. So it is going to go even higher this time because we're permitting the same amount of time. And then when it goes back off, I figured out right where this is going to go, but you continue to not fall to the lowest point. So you have this stacking cumulative effect of like your lowest possible voltage is slowly going up and your average voltage, which if you smooth that further using capacitors and inductors with your load, sort of, in an ideal world, then you can kind of smooth that out. But you can see if you're doing this incredibly fast, this is microscopic, but it really kind of just ends up being like small, and it goes up and reaches its equilibrium point. The equilibrium point is determined by a mathematical equation that is not really important here. If you want to look at it, it's on Wikipedia. But again, this is the tool in your toolbox. This is not how you manufacture a wrench. This is merely telling you that this wrench exists. Any questions?
Okay, so as the voltage is going up, it's because the current is being stored in the inductor and it can't release it as much because of the resistor, but then it turns back on and then there's extra.
Yes.
And it's flipping back and forth.
So I should point out that the voltage here, we're measuring it at effectively this point. Because there is a resistance to, or the impedance, because the inductor is resisting and changing current, it is technically, initially, we sort of covered this in the first day, we sort of didn't. If you look at time 0 on this, you're supplying 5 volts and this is dropping 5 volts. It is using all of the power you're supplying to it and it is allowing like no current through this whole process while it's building the current up. So as like if we allow it to get to steady state, which we is almost but not really do, we're cycling too fast for that, then this would go down to like dropping no voltage, and this would just be the same as the input.
Because it becomes a wire, or close to a wire.
Yeah, effectively. Once you've built the field up, if you were using pure DC and not doing crazy stuff like we are, but because you allow it to like build up this rapid field and then you stop it from going this way until it has like a lower current that it wants to be at, it discharges its field because it's storing, it cares about like current more or less. So it wants to conserve its current. This diode is just here to make sure that when this is discharging, so in the on cycle, when this is shorting this way, you have a little bit of stored energy that's continuing to provide power. What's up?
How to control the out?
How what?
How to control the out?
Oh, it's the same as this point. So these are electrically equivalent. Well, I guess except not when you're shorting this way. It's not really electrically equivalent. So really, this is a voltage of this part right here. It's one of those things where like you're charging up this capacitor, and then just you're taking away power so briefly that it doesn't fully discharge, but you're then reapplying power before it can discharge. So like this is your voltage out. It's yeah, and yeah, you can see it overshoots it a little bit, which is a thing that you can for your transforms and calculating a better like impedance matching. You can make sure it's better damped, way beyond the scope of what we're covering. But yeah, any other questions? It only gets more complicated from here. Okay, so this is probably the last easy to understand circuit that we'll go through. If we have to step up our voltage to supply our reaction wheels for the CubeSat and for the weather balloon, this is probably what we use. Because you're just shorting the ground, these are kind of low efficiency, but for example, these apparently are used in Toyota Priuses to go from like 230 volts to 500 volts for their motors. So I guess if Toyota doesn't think the efficiency loss is that bad, then I probably shouldn't be too worried about it either. The main reason that I did not start with these when we were making our own thing was that if we're coming off the battery for the first time, this voltage is also changing and things get really hard, and producing a stable 1 kilohertz sine wave, it can be difficult again with variable voltage until you start just saying you just want to buy a jet to do that. So doing that from individual components is a little bit beyond my enthusiast level of knowledge. So yeah, because it took me a long time. I was searching for a long time trying to find a way to create a stable sign or a stable input wave for that, but didn't seem like it was going anywhere. Which we'll actually look at one of the other things I was thinking of for that in a second. Yeah, basic use, increase voltage. Done. Any last minute questions? So, dude, you are so well dressed all the time. It is amazing.
Thank you.
So why is it inefficient to short the ground? Is it
Well,
because you're losing electrons?
Because you're just shooting like the battery's power down the drain effectively, right? Like sure, you're charging up this inductor, and this inductor is going to spend a little bit of time like resisting that. But if you hook a battery just up to this negative terminal, it's going to get extremely hot and be painful to hold on to, but it's just going to Like the electrons want to move from this end to this end, and if you tell them that there is no resistance on the way through, they will move that way very fast, and all you will do is convert your power into heat in an incredibly rapid fashion.
Yeah.
So every moment that this is shorted to ground, you are just losing power and converting it to heat effectively. So that's why it's low efficiency, is because a certain fraction of your normal cycle of this is just blowing power to charge that inductor.
Okay.
Yeah. Any other questions? All right, cool. If anything else comes up, then feel free to mention it. Okay, so here are some other transistor types. These are 3 of the most common other types of transistors, and they sort of have uses for application, which is why they're on here. Bipolar junction transistors are probably the second most common type of transistor. So here, junction transistor, not field effect transistor. You can see that schematically because it is connected here. MOSFETs are controlled by voltage. These are, in an abstract way, also controlled by voltage, but what truly matters here in terms of how much current they allow through here is how much current is going this way. Or I guess technically this way. I'm more used to NPN. Oh, which also, that's a good point. This goes back to the PNN temperature as we briefly discussed with the diodes. It is, the only thing you need to know about this is convention and to be aware they exist and to find the right one. But schematically, NPN, not pointing in. That's the easiest way to remember it. And then the other one is, pointing in. That is important because bipolar junction transistors do care about which way flow is going. They are like diodes that you can turn on and off to some degree. But we mentioned earlier about gate valves with the MOSFETs, and that if all you have is like a gate that just kind of slides up and down, that's like actually not good for throttling, kind of. These are more like throttle valves. So they have a very linear relationship, which is why they are used when MOSFETs are like 99% of everything. So I'm gonna erase this if nobody else uses. So, like I said, the important characteristics for bipolar junction transistors are the current between these points. So this is what controls the throttling. I guess terminology-wise, I should quickly explain something. I will say what these are. It doesn't really matter to you guys. It's gate, drain, and source. Or source, gate, and drain. They kind of speak to what they are themselves. The gate terminal does the gating of it, turns it on and off. Source is where it's coming from, drain is where it goes generally. MOSFETs generally will allow conduction in both directions unless I'm misremembering, which I might be. But collector, emitter, base, much more inconvenient to remember, but that's what they stand for. So yeah. But anyways, so what determines your throttling effectively is your base to emitter current. So we have a nice linear relationship of base to emitter current, IBE, and collector to emitter current, so ICE. It's literally just that. The magnitudes aren't important here, the characteristics are. It's linear. The MOSFET is not. It's kind of more like that, and it's not great. So you can use both of them, and we will see both of them. MOSFETs are better for like turning things on and off. BJTs are very useful for like if you need to have a very linear relationship between things. So they were and still are very common in amplifiers for like music and stuff. The schematics of these will always look terrible because you're really doing this for like, if you think about your equalizer in like a car or on like a stereo or something like that, how it might have, it will allow you to change the gain of like 2 hertz to 10 hertz, 10 hertz to 20 hertz, 20 hertz to 40 hertz. each one of those is a different transistor, and all you're doing is modifying the gain by selecting some biasing there, which basically says like, I want it to multiply by 2, I want it to multiply by 4, I want it to divide by half, or multiply by 1 half, you know. So basically the schematic in that case is like a whole bunch of these with some variable resistance that you can set remotely. So yes, we will see these in a circuit here because their linear relationships are very useful to us, but a lot of it is kind of MOSFETs. So this is a unijunction transistor. This is even more so than a MOSFET, literally just turning on and off. There is no throttling, it is all or nothing. I don't really know why these are so far out of favor. I think, well, actually, I guess I do know why, because as you can see here, they're another junction one, so you're losing, this signal has to supply current, which is not always convenient. We're not really gonna look at anything with this, but if you don't mind having your signal using current to supply something, then it's a very useful, very rapidly switching on-off switch. And this is an insulated gate bipolar transistor, commonly known as gigabits. The only thing you need to know about this is they're very useful for high current applications, which in the world of transistors, high current is like a couple of amps, but these things, you get enough of these things, you can handle 1,000 amps. They can, especially for like semiconductor technology, they're pretty impressive. They're very useful for high voltage stuff. I don't think we'll see them in the CubeSat, but I don't know. I wanted a third thing to put on the slide, I guess. And I didn't want to talk about SCRs, and I didn't want to talk about, I don't know, other things. Any questions before we move on?
What would 1,000 amps even look like? I can't even.
Well, I mean, for example, on some of the United States, Los Angeles and Ohio class submarines, instead of having, right, they have a giant battery and they have a giant AC distribution system. In order to convert power between the AC and DC systems, for older ones, they literally have a giant DC motor connected to a giant DC generator. And like, so you use a DC motor to make an AC generator, but they're wired up so that they can also be an AC generator or an AC motor to a DC generator. They're called motor generators. But all you need to know is they can convert DC to AC or AC to DC back and forth. If you're using, you can do that with inputs, static, solid state. So we had, my boat did not, but at one of the places I trained at, we had what we call servos, static electrical reversible power supplies, and they used a whole ton of egg bits to do that. Sort of the equivalent of a high power version of a UJT, the unijunction transistor, are SCRs, silicon controlled rectifiers. They're basically giant diodes that you turn on and off remotely, and then there's a lot of other stuff out there.
How big is giant?
What do you mean, like giant in terms of?
For a diode, like what's
Well, your average diode is like,
it's
it's
tiny.
incredibly tiny. An SCR, I've seen SCRs like that big, you know, quarter-sized dish, but thicker. Yeah, I've seen 8-bit arrays that are like drawer-sized. So yeah, these things are robust. The entire servos were about my height and 8 feet long, I guess, and 2 feet deep. So cool. Any other questions? If you guys want, we can go look at a list of different types of transistors on Wikipedia after this. Alright, so BJT applications, multivibrators. So these are, it depends on the type. We're actually probably going to start with bistable because I think it's the easiest to explain, because astable is really hard to explain, and I don't know if I'll even try because even Wikipedia's description is awful. There are no good YouTube videos for it. It's going to be the first one where we kind of just go, I believe. So this is a bistable multivibrator. What you should take from that phrase is that it has 2 stable positions and it will vibrate between one or the other. In this case, since it is triggered specifically, it's kind of like, it's not vibrating on its own, it's you induce it. But what you should take here is, at first, like the condition that this is representative is that we have this positive voltage here that's coming in. And basically this positive voltage, so like we talked about the gate or in the, for BJTs, if there's a voltage present here, they conduct. Similar to the MOSFETs, if there's voltage on the gate, they conduct positive voltage, not negative voltage. Negative voltage will do the opposite of that. So what we can see here is plus V is all the way over here. Q2 is currently not conducting. So that's why it goes from max voltage to no voltage, as represented by the blue. You have a positive voltage applied here. It is conducting. So because it's conducting, you're dropping all of your voltage across this resistor. Is everyone with me so far? I need to take this like really step by step because this gets kind of not great. So high voltage on gate, this is conducting. Because this is conducting, all voltage drops here. 0 volts here. 0 volts on this. This is not conducting, as we can see. In a static, like, equilibrium situation like this, it's very easy to understand. When you go over to that one, it's a lot harder. But basically what you do here is, if you want to swap states, you shut this. This goes to 0 immediately, which means this stops conducting, and now you have a bunch of voltage here while this is being shorted. That voltage is no longer 0. You're not dropping anything across here, there's no voltage through it. But you do now suddenly have positive voltage on this, and this begins conducting. Does everyone follow that, how it swaps? So you press a button, this turns off because you're shorting the base to ground, and it flip-flops is actually what these are called. So sort of, there's 2 names for kind of the same thing.
So that means like if you use this switch, the negative becomes positive and positive becomes negative.
Well, in terms of the bases, yes, except not negative, just 0. And so, you know, this circuit is not doing anything useful, really, but what you might have is just this voltage over here is being sensed by perhaps a MOSFET with infinite impedance, right? So if you have this being positive right here, locked in, it's gating some MOSFET, and that MOSFET's telling like something to do over here, right? Whereas this one would be nothing, the MOSFET would not be gated, it would be turning something off over here. So you could use this like if you wanted to reverse the direction of a motor, right? Because you care about the direction in which it flows, you could wire something up where it's like, well, if this is positive, current goes this way. If this one is positive, current goes this way. And if you've got them wired up in opposite directions, you're turning the motor in different directions now.
Okay.
So, yeah.
So this new voltage drop across R2
What's
after
it?
it's flipped.
Yes, yeah. So after it's flipped and this is conducting, then all the voltage drops across this. This is now 0 volts in this direction, so this remains shut even after this reopens. So this is a transient kind of button. You're pushing something, and it is shorting this just long enough to make sure that this stops conducting and this starts conducting. So, yeah. And this itself does not do useful work, but it does create a system where you can say, you know, I press a button and it swaps between 2 things.
So then you can like oscillate the motion of something.
Sort of. We'll talk about with this one specifically. This one doesn't even need a push button. It just continuously does that, which makes it a better version of the LC tank that we talked about. But it's also really difficult to understand, so we're going to start with this one because this one's like a lot more self-explanatory.
So, I missed last time, but why are those conducting? What piece of equipment is that that's allowing it to conduct, and then not the other one?
Well, that's all within this meeting, but you did miss kind of the first like 5 minutes of it. They are just they're the mechanical equivalent of like a valve that you can operate by like applying voltage here. So like the way I described it on the first slide was a solenoid operated valve, which the word solenoid probably does not necessarily mean a whole lot to you, but solenoids are like you apply voltage and really you send current through them and they make a giant magnetic field and it'll like yank a valve up and down or something like that. So, yeah, basically the idea you should get from that is with all of these different types of transistors, is if you have a positive voltage on the like side thing, it conducts. That's really the main takeaway from that. So, okay, so that's too far. Okay, so yeah, so that is the bistable one. That one's the easiest to understand. Things get a lot harder with monostable. So this is similar to bistable, except the idea behind this is when you press the button, it'll short this one and it'll swap to the opposite state. But this capacitor here is going to charge while that's happening, and eventually it will by itself swap back. So that's why it's monostable. One stable state with a transient state. I can't think of anything right now where this would be like definitely useful to us, but it's like if you want to, if you wanted a trivial example of it, it's like if you wanted to push a button and a light would come on in 5 seconds, or it's like a doorbell, I guess, if you wanted to ring a doorbell and have it send a buzzer for 5 seconds, no matter how long it was, well, assuming they stopped pressing the button, basically, then that would be like kind of a use for it. So the capacitor makes things a lot harder to explain, which is not great, but so the normal state of this, using a very similar kind of principle, is that we're going to start out with Q2 conducting. So with Q2 conducting, you're going to have current going this way to ground. All of your voltage is going to get dropped across R3, 0 volts on Q1. Everyone with me so far? In the meantime, on the other side, right, because this is conducting at some voltage, there is a very careful balance of your resistors and your capacitors here, where basically the ratio which you set this will produce some voltage across this capacitor. And when you short it to ground, it's going to begin discharging. And yeah, so basically when it swaps states, so you short this to ground, this stops, you're now dropping nothing across this, so your potential is now here, this gates, and this will start to discharge. And once this turns off, there's basically like there's only a certain amount of time before this turns back on, which is dependent on your capacitor discharging. I feel like I didn't explain that very well, but it's also, like I said, it's just very difficult to explain. There's honestly not that many good YouTube videos out there for it, and this is kind of where we start to enter the just I believe button of like, the atoms in the wrench are shaped like a crescent. I don't need to tell you how they get machined.
Okay, but what it is actually doing is it's like you press it and it like turns on for a little bit and it like decays down and then it's off.
Yes.
Okay.
So the main takeaway is like, whenever it is commanded to change states, it will change states, and with no further input, after a short delay, it will switch back. That is the main takeaway of this. And again, it's just being aware of what's in your toolbox. I don't know, this is something you might have a use for, or not. So, potentially more useful is the A-stable. So we're already getting a lot more annoyingly complex. And it's similar principles of these capacitors are going to like hold a voltage on them, on the gate of, the base of these bipolar junction transistors, and they're going to allow them to slow or like at a specific rate turn on and off. You can by, if you set R1 and R4 and R2 and R3 and C1 and C2 to the same values, you will have a perfectly like 50-50 duty cycle. Duty cycle meaning like on and off. I guess that's probably the easiest way to say it. But you can alter these. You can have it so that it is conducting like disproportionately, which is to say BJTs, we mentioned them being fairly linear, and these generally are used for creating like, well, let's call it 0. with no DC offset, you can use this to create like a triangle wave. If you want to, you can offset this and have it like rise really rapidly, lower, slower, rise really rapidly, lower, slower. So you can do some like interesting wave shaping stuff with this, basically. Usually everything is happening small enough in the, like to the degree of like we mentioned time constants earlier. Usually this is happening fast enough that it seems linear, but realistically with capacitors, right, they follow a logarithmic charge and discharge cycle. But usually you make a point of choosing capacitance values which are suited to making something like that, kind of. Any questions?
So, is this what like the square root form generator does? Because it takes all of these like astable things.
I think it uses it in part of it, but it's going to then use this to drive something else. Like if you set it up right, you can have it so that it will, like if you fed this into, well, you wouldn't want to use a bistable for this, but you can have it feed into something that will do instantaneous switching. So like if it was driving something else, which at the top of its wave at 5 volts, whatever, if we're doing plus 5 volts and like minus 5 volts or something, you can have it so that at minus 5 volts, it swaps something over, which causes that to swap polarities instantly.
Okay.
So yeah, this is usually for creating like triangle waves, or like really sloppy sine waves, but we'll see triangles. Any other questions? Okay. What's next? I think I made this pretty. Okay, the amplifiers, we kind of mentioned this before. There are MOSFETs and BJTs have a slightly different method of doing this generally, but realistically, you can kind of, it's a matter of creativity to some degree. So for the MOSFET, what you'll notice is that your voltage is coming in and it's actually like kind of shorting this to ground, right? So we're operating within kind of like we've opened the MOSFET, but we're trying to throttle it and we're just usually not doing it that great of a job, sort of. But I'm trying to decide how much detail I want to go into with this. The big takeaway is you'll notice here that the input signal, your polarity is swapped on the way out because you're kind of shorting more and more to ground the more you open this. And that's kind of generally how MOSFETs are used for amplifiers. But really all you need to know is amplifiers exist. So there's not, I don't really know that much more into it. And you're gonna have the opposite thing here. So in this case, with BJTs, it's generally like reverse polarity. You can account for that. You can, write this sine wave. If you just wire this up the other way around, you are looking at the same signal more or less effectively. That's the wonderful thing about electricity is it's all about point of reference. So if you wire your thing up and you have a reverse of what you want, you just swap the leads. So it's still useful, but what's up?
Or could you just like phase it all the way through like a full cycle?
Yeah, you could also phase shift it. Phase shifting is hard, especially if you're going to be dealing with any sort of variables with regard to it, because it's going to, the amount you phase shift will change for every change in resistance, inductance, and capacitance. So because this is like technically representing some form of impedance as it's throttling, that just gets really hard and annoying, and it's generally not what you want. Or you could just put another one on the end of this and have it set to a gain of 1 and just flip it again. So, yeah. So with this one, because it's kind of like the more, this is an NPN type. So basically like the more you open this, the more current is going through this, so the higher voltage is sensed here. Any other questions on this? Again, we're getting a little hand-wavy here, but this is the point where an analysis of individual components is starting to become more effort than it's worth, and it's more just an introduction of tools for you. You can make your own amplifiers. It's actually not that bad. There are a lot of guides online to doing it. Or you just buy an amplifier for like $5. So it's just depends on you. Okay. Transistor to transistor logic. This is a little bit of a weird departure because Presumably you have all heard of binary, but do not necessarily know what that means. But this is our first kind of foray into what binary is. Binary is 2, right? Which is to say there are 2 states, on and off. And you can do everything you want to off of that. You can literally determine everything by whether it's on or off. If you have 4 to 8 characters, depending on what system you're using, you can do the whole alphabet in 4 systems of on or off.
2 to the 5th, right? Or 2 to the 4th?
2 to the 4th for 4-bit, yeah. So 2 to the 4th is 32, I think. 16? Yeah, 16-bit. Yeah, you're right. But with 16 on or off, well, okay, 16's on or off, so it must be 8-bit. But yeah, generally 8 is enough to express any word that you would need to do by saying like, oh, A is equivalent to 0, 0, 0, 0, 0, 0, 0, 0. But aside from just basic stuff like that, logical statements of on or off can also be used as like comparison things. If you only want a signal to be sent when 2 signals are present, use an AND. Or if it's 3, it's AND. If it's 4, it's AND. You can hook up any number of inputs. It will only output when you've done it. This is a colossal pain in the ass to do schematically. This is a NAND gate, I think is what it said. Some of them are simpler than others. Like NOT is really simple because NOT is just, well, I think it's just a transistor basically. And basically all it does is you have, well yeah, that's probably the easiest one to quickly describe this with. And that'll kind of give you guys the principles of operation for most of this. So a NOT gate is basically just a MOSFET or a BJT either way. 5 volts and out and ground. Imagine some resistor here maybe or something. And this is like your input signal. So a NOT gate in this case, if you put in a logic 1, which in this case is 5 volts, so you apply 5 volts to this, this turns on and conducts, this shorts to ground, all the voltage is dropped here, this is shorted to ground, this says 0. So you put in 5, digital 1, you've received 0, digital 0. So the converse of that is if your input is nothing, this is not shorted to ground, this drops no voltage, and this is now 5 volts out. This is all again kind of relying on like infinite impedance outputs, so you hook this up to another MOSFET and that would do the actual work of it, because otherwise you send actual power that way and you don't want to do that. But that's the most simple concept of like what we're doing with this. So you can do stuff like OR, if you want to send a signal when anything is happening to just like do some command, you can do that. Most of the time processors do this today, like we just do code these days. But if you want to be like cool and old style and to like actually use real gates, you can find these, you can get them. NAND gates are, hold on, I don't know if that's a real gate all of a sudden. Exclusive AND? I think that's the same as a NAND. NAND is the opposite of AND. It says if anything is present, I turn off. Like if you think about AND, everything must be there for it to send it. For NAND, everything must not be there for it to send it. Does that make sense to everybody? NOR is kind of the same thing. It's just an AND gate with a NOT attached to the end of it, I think. That might be actually the exact same thing. NOR. Fitting one signal. So that would do the same as a NAND. Maybe NAND is if all of them present turns off. I don't know. Anyways, you can look them up. But it's called transistor to transistor logic because it relies on transistors doing things. Does all that generally make sense as like this is a thing you can do with transistors? Sorry, it's not more detailed, but realistically, you don't ever see the internal diagrams of these. You just see I need an AND gate. This is an AND gate. I need an OR gate. This is an OR gate. I need a NOT. This is a NOT, an exclusive OR. You never really look inside these things, and that's going to be again more and more the case. Is we're going to stop looking inside the box, kind of here. And this is an op amp. This is what we're going to be doing next time. I don't know how this works. This is a magical Dorito. You can technically go through and do a circuit analysis of this. Op amps, there's a million different types of op amps, which is why they get their own lesson. And this is probably one of the only times you'll ever see the internals of an op amp, because everybody just draws the magic Dorito. So, almost all op amps, in terms of simple ones at least, are schematically represented like this, except most of those also get rid of these because they're just implied. But what we'll talk more about next week is like, this is basically your positive power supply. You will see it called different things, but what you should take away from that is like, this is the positive, and this is usually ground, unless you're doing something funky, then it is your negative power supply, usually with like the same positive voltage but negative down here. And then you have a non-inverting terminal, which is an annoying way of saying positive sort of fits. We'll get into more next week. And then you have an inverting terminal and your output. You can see those here, along with some other things. You have a non-inverting input, you have an inverting input, you have your V supply, you have your out, and you have your V supply negative. And then this one has offsets. We're not going to look at that for now. As you can see, there are a bunch of bipolar junction transistors in here. Doing an actual circuit analysis of this is pretty hard, obviously. I don't even want to attempt it. So, and in actually trying to like do it on a electron to electron, second to second basis would probably take hours. So, yeah, this is kind of just here to really drive home the point that we've explored very simple things so far. In reality, things are pretty darn complex. So, you can do a lot of very useful things with op amps, and we'll probably talk about that next week. Does anybody have any questions? That's pretty much going to wrap it up. So, again, op amp or transistors, what you should mostly understand is that they're a way to use either voltage or current, depending on if they are field effect or junction transistors, to remotely activate a circuit, sort of, or to turn portions of the circuit on and off in some sort of coordination that you determine. Yeah, the boost chopper is probably the coolest and easiest to understand part of this. Any last minute questions? Cool. Next week is going to be op amps. Op amps stands for operational amplifiers. Operational in this context means you can do math with them, and by math I mean you can do calculus with these. They're literally integrating and differentiating op amps. We are probably not going to look at the internals of those op amps ever again. Most of how you use op amps is determined by the components you put around them. Yeah, but if there are no questions, then that wraps everything up. And do I just hit the escape button, guys? Cool. And yeah, hopefully I will see you guys next week. And I'm curious to see if my phone is still alive.
Yay.